So how do you go about proving that two groups are not isomorphic? Well, there's probably lots of techniques, and Barnard in his text gives one approach which is quite powerful and quite general, and at the end of me explaining this to you, I'll show you how you can apply it, and you'll be probably quite surprised. It really is quite a powerful technique, but I'm not saying it's the only one. There's probably lots of tricks that you can use to show two groups not isomorphic, besides the obvious one, that is when they have different orders, when their two groups have different orders. Okay, so the trick, the method given by Barnard is that you take your two groups and you ask yourself, choose a particular integer, and I say 4, whatever, and then ask yourself how many elements in the first group. So we're talking about. So try a different pen. And the question is whether these two groups are isomorphic or not. So choose a particular integer. It doesn't really matter which one it is, just an integer, and then go looking for those elements in your first group and your second group, such that, so let's say you choose your integer n, okay, and then go looking for elements belonging to G, and let's say elements Y belonging to H, and ask yourself how many of these elements in G and how many in Y are such that x to this integer that you chose equals the unit element, and for Y, for the same integer, would be the unit. Well, yeah, I better put a little g down here and an h here. So this is the unit of group H, and this is the unit for group G. Okay. Now you may say, why on earth talking about this? Well, it turns out it's quite a powerful technique, and so you look at your elements in G, and you check whether that element, whatever it is, let's say the order of the two groups, I don't know, P, whatever. Now they have to be the same, of course. The orders of both have to be the same. If they're not, then you know immediately they're not isomorphic. So they'll be the same. So check for all P elements in G and for H. Check whether each element, when raised to the power this integer, some arbitrary integer that you choose, and see if it results in the unit for G, and similarly the same n, similarly for group H. Okay. Now the test is whether two groups are isomorphic or not. Well, to see whether if they are not isomorphic. The test is you count the number of elements in this set that obey this property. In other words, when you raise to the power of integer n, you get the unit. And similarly, you count the number of elements in this set that also have this property. So let's label these two. Let's create two sets. So T of G, by definition, is the set of elements X that belong to G such that this property is true. So x to the n, little n, integer n, is equal to E of G. That's the unit of this group. Okay. And similarly, we can so what is that? It's the set of all your elements in G that have this property. Okay? Now you you know where I'm going with this for a while. Just trust me for a while, but it works. But I need to define some terms. Okay, so here's another. This is the corresponding set for group H. So try another one. Oh, by the way, this evening I will very probably get my new board. So this will disappear. It'll be all nice and white. It'll be the same height, and it'll be about 30 centimeters longer. Right? So I'll have a lot more space. And since I've learned not to rub, I've learned to wash. So the white surface should stay a lot longer. Now it's the same company, so it'll have this silver undersurface, which is pretty stupid, given that you want it to be white. But still, the price of these boards is about 1/10 of what a high quality one is. So I reason it should be cheaper for me. If it does get like this again, well, I'll just buy another one, right? And it'd still be a lot cheaper than buying a high quality one at 10 times the price. Probably imported from the West, so hence the high price. Okay, so create a similar set of these elements Y that belong to the group H, such that they satisfy this property. In other words, the element to raise to the power n, some arbitrary n, gives it the unit element of H. So this will be Y belongs to H such that Y to the n equals the unit of H. Okay? So you're talking about two sets. Alright, now before I get into an actual proof, let me sort of give you the big picture kind of thing, the motivation. So here's the theorem. Although it's not a theorem number in the text. It's just but he does prove a theorem in effect. But here it is in words. If these two groups are isomorphic, then the size of these two sets, the size of T of G and the size of T of H, are the same. Okay? I'll say it again, because if these two groups are isomorphic, there's a theorem, well, it doesn't have a number, but there's a theorem, you can actually prove that the size of this set, in other words, the number of elements X that belong to G that have this property, the size of this one and the size of the corresponding one for H are the same. Okay? So if isomorphic, the size of these two sets is the same. Now, so in general form, so if P then Q, or I could rewrite that like if isomorphic, same. Put it that way. Forget about this. So if these two are isomorphic, then the size of these two sets, the number of elements that have this property, is the same. Right? Okay, so you test that. You go finding the size of this set in G, you go finding the similar size of this set in H, and you look at the number, how many elements in G have this property, how many elements in Y, how many elements Y in this group have this property, and you compare. Are they the same? Now if they're different, so with this logic, so if not the same, then just by simple logic, therefore not isometric. Okay, so that's your test. This is just well, the example I usually use, if you live in Xiamen, that's the city where I live, where I make all these lectures, you live in China, but you don't live in China. Right? If you live in Xiamen, you live in China, but you don't live in China, therefore you don't live in Xiamen. Right? So if isomorphic, then these two sets have the same size. Okay? But say you test them, you go looking at each element and you find the number in this set and this set, and if they're not the same, then you know these two groups are not isomorphic. Right? So you've got yourself a test. So that's sort of the big picture. So now I will now go about proving that that's the case. So in other words, I'll prove this. Right? I'll prove that if these two are isomorphic, then the size of these two sets is the same. Right? So I will now do that. The proof is on page 96 and 97 of your text. Be warned a little. I had to scratch my head a bit. I felt there were. There's quite a bit between the lines, so to speak. Often, look at the proof and say, where did that come from? So it made me think. So I was adding notes in the margins to myself to help clarify the proof, and I'll give you those notes because without them, it's not so obvious at times. All right. So the point of the exercise is, given these two groups are isomorphic, we have to show that these two sets, or in other words, the number of elements in G, this group, that have this property is equal to the number of elements in H that have the corresponding property, right? For the same n. And it could be any n. Right? This proof, if isomorphic, then this equals this, is true for whatever little n you choose. Whatever n you choose, whatever integer you choose. It's a general proof. Okay. So let's try to prove that. All right. Now